Hi everyone, my name is Karago Antreja, and I'll be presenting our project, the Multimodal AGI Partial Discharge Diagnostic System. This project aims to detect and classify partial discharge in high voltage electrical equipment. Besides detecting and classifying partial discharge, it also locates where the partial discharge has occurred in the system. So in this presentation, I'm going to describe the data sets, the processing, and the data input into the models, the 4 different model architectures that I used, and the explanations of the results, my conclusions, any limitations I faced, and acknowledgement. Partial discharge is an electric spark that occurs within the insulation that can lead to the degradation of the insulation in high voltage equipment. When this insulation degrades, the chances of the short circuit increases, and when short circuit occurs, intense heat is produced in the high voltage wire or in the transformer, leading to fires and loss of equipment. So these are the results. In these images, you see the results of the partial discharge, which includes the wiring of the wires and also the damaging of electrical equipment. So the models that I explored are a graph neural network, which was a spatial temporal graph neural network, a fusion-based multimodal stacked ensemble model for partial discharge. This utilized the light gradient boost model, and then the PD neurosymbolic model that used three-dimensional convolutional neural networks, and the PD localization model. So the last two models, I had described them in my previous videos, but then we're going to go into the first two models in depth. So what does our data look like? I have over 8,000 files that are equally distributed between partial discharge, chaps, and white Gaussian noise. The sampling rate is 96 kilohertz. The duration of 50 seconds, and that in each of those 50 seconds, there are 10 repetitions of each of the sound types. They're collected across 90 volt locations on a 32-channel MEMS microphone. And then for the electrical partial discharge data set, we have 347 controlled partial discharge acquisitions of corona surface and internal partial discharge. These are types of partial discharge that have also been sampled at a high rate, as you can see. So for the model one, which I'm going to describe first, will be the spatial temporal graph neural network, whereby the dataset was processed to produce the time domain features, the spectral features, and the spatial features. The spectral features reveal the shapes of the graph, of the waves, the different sound waves. The spatial features reveal the location of the waves, such as the time difference of arrival, how the waves traveled between the microphones. And then we have the time domain features, which reveal the properties of the waves, which include how the shape of the wave, the energy the wave has. So the input data structure. So the nodes are created whereby each of the 32 microphone channels are treated as nodes. And with these nodes, each of these nodes have each of the 8 features that you have described above. So the labels are the white Gaussian noise, the chaps, and the partial discharge. And we have also the locations which show the spatial locations of the source. So the first stage in our model, the graph is constructed whereby the raw nodes and the features are normalized, which means that they're put in the same scale, whereby we would not have features that are either too high or too low. And then the time difference of arrival is calculated between the different microphones to see the time taken for each wave to travel between the different microphones. And then we have the graphs are built whereby each microphone is connected to its 6 nearest neighbors. At first, I had tried to have the microphones all connected to each other, but then that produced poor results with a poor performance. But when I used this, I got better results, which shows that the microphones communicate more to the nearest neighbors. So after this is produced, we have built the graphs. They are all packaged into a data object, which is passed into the graph neural network. So when it's passed into the graph neural network, it undergoes 3 steps. There is acoustic message passing, whereby you have this information, these 8 dimensions passed from one node to another. So once this information is passed from one node to another, you find that some of the nodes were able to capture more information, or were able to capture information that had a higher importance. So that's where the attention weighting comes in, and that comes in here in the graph attention, the GATConv layer, which pays more attention to the nodes that captured more information and gives them the higher weights. So here we have four heads, the distribution across 4 heads, whereby you have the 64 dimensions are expanded to 256 dimensions, which means more features are captured, or the more features are analyzed as these messages are being spread between the nearest neighbors of the graph. So you can imagine if a node is connected to six other nodes, you see it's the features are being spread and then compared between the nodes, and then we are finding the nodes that have the higher feature values, or that have captured more information, and these nodes are given higher weights. And when they're given the higher weights, we're able to then pass, after giving the higher weights in these attention layers, as you can see here, the GAT convolution layers across the different heads. So why do we have different heads? We have different heads because each head focuses on a particular set of features, so that each feature so that each feature is taken care of, or it's looked at, and the weights are distributed accordingly. So after that, we go to the global mean pool layer, which gets these results and averages them. And after averaging these results, they're all passed to the classification heads. In the classification head, you find that they're passed to the linear layer. The linear layer reduces the features until we end up having the probabilities, the 3 probabilities, which are the probabilities that represent the 3 different classes, which are the partial discharge, the chaps, or the noise. And then in the localization head, we find that they have been reduced to, say, 90 probabilities. In the 90 probabilities, each of them represents the location of the sound source. So this is how the graphical neural network works. So it's just 3 simple steps. That is message passing, by the nodes communicate to each other by passing messages to each other. So when they pass messages to each other, the nodes are able to identify, say, a specific node has gotten the signal better, or has gotten the features better, or has higher features. So after getting the node that has higher features, this node is given a higher weight. When the node is given a higher weight, you then pass this information to the classifier head, which is able to classify the information to say that this node picked say, partial discharge better. This is a probability that you are predicting partial discharge based on the information that you have gotten from these different nodes. So how does the model learn? So the model learns in case there are 2 ways the loss is calculated. So this is calculated via the classification learning, that's cross entropy, whereby in case there is a wrong prediction, there is a higher punishment is given, and the loss is really high. And then for localization, we use regression, whereby we use mean squared error. So the total loss is we give a higher loss count to the class. This enables the model to learn the classes first, and then to learn the location. This was given because in previous iterations, we found that the model was learning locations faster than it was learning the classes. So that's why we had to make this adjustment. And then once this loss is calculated, we carry out backpropagation. Backpropagation enables you to see where the error was originated in the model. So once you see where the error was originated in the model, you're able to adjust the weights and using the optimizer. So we use the Adam optimizer that adjusted the weights in order to reduce the loss in, say, the next epoch or the next cycle. So this Adam optimizer also came with weight decay, whereby large weights will also reduce in order to keep the model flexible. Whereby if you have a features that have really, really large weights, we don't want the model to focus on only those features. We want to keep the model balanced. And these were the output results, whereby we had a high accuracy for a classification of 99%. The localization had a really low a really low error. And then we have the confusion matrix, and then we have the localization error, whereby we have a higher count of the errors going to a lower value. And then we have the true location, we have a linear relationship, which shows that the model really learns the location or the location relationships. And then we have the output results and explainable AI, whereby we see how the signal is spread. The signal was spread evenly across the different nodes or different channels, and just the microphone sensitivity, whereby we have different channels having different sensitivity to a signal. So that's, for example, the class was 0 in case, so different microphones have different sensitivities to partial discharge. And in the different microphones here, in the last graph, we see that different microphones also offer different contributions, with some microphones having a higher contribution to the prediction of partial discharge in a given sample. So the parameters of this model were the attention coefficients, which are the weights, the attention weights that were given in the attention layer, and then we have the linear transformation weights, which were the weights given in the linear layer that the model learns and updates from the data. Then the hyperparameters, these are parameters that we set ourselves. So we have a slow learning rate, we have the weight decay that we set, we have the loss weighting for the location, where the bus rate, and then the patience before you stop training. So the second model is was the ensemble model, which used gradient boosting. So here with this data set, we're able to also derive the time domain features, spectral features, spatial features, and then we're also able to get some statistical features. And then here we have the time domain features, the spectral features, and the pulse features from the electrical partial discharge data set. So with this model, first of all, we got these features and we inputted them in the different expert models. We had 3 expert models. We had a signal classifier to differentiate between partial discharge noise and chirps, which was the light gradient boost model. We had the localization model. We had also an electrical model. So once these models make predictions, we'll have a gatekeeping logic to make sure only the probabilities of the partial discharge we entered into the feature matrix. And then we also make sure that the confidences were also entered. So that's why we have the signal, the acoustic partial discharge confidence, the location probabilities, and the electrical probabilities being entered into the feature matrix. So from the feature matrix, these values are entered into the final fusion model, which is a physics-guided light gradient boost model. Once they are entered, these probabilities are trained and able to produce the final partial discharge type prediction. So with this final prediction, you have the partial discharge type and the location of the partial discharge being produced. So you find this model carrying out 3 different tasks. That is classification of the acoustic signals, classification of partial discharge, and getting the location of the partial discharge. So these were the output results, whereby you had the overall accuracy was 95%. This was a confusion matrix of how the difference, the results of the validation. And then from the explainable AI, we see that acoustic location has the highest contribution to predicting, to the predictions. This reflects the fact that surface, internal, and coronal discharge all happen at different points of electrical equipment, with corona being in the air, internal being rather inside the equipment, and then we find that surface is usually on the surface of the high voltage equipment. So, and these were different contributions, as you can see. How the model learns, we had the optimization, we had a low learning rates, we had many trees being employed, we had visualization in order to prevent model fitting, we had to limit the model depth and trees. There was data sampling, whereby different trees were given different samples of the data, and also different trees were also given different samples of the features, so that these trees can actually learn the different patterns in the data. And then we had early stopping for the fusion model in order to prevent overfitting again. So the parameters that we optimized, we had the split thresholds, how the leaves are split. Remember, it's a light gradient boost model, so the model is split leafways. There are leaf weights, how the trees are formed, and the feature selection. Which features are we choosing to split? And then here we have the hyperparameters. That is the learning rate. We had the maximum depth feature fraction, the bagging fraction, which we chose. What percentage of data will be in each tree, and then we set them in order to aid how the model learns. And then if you had to go to the earlier models, the PD neurosymbolic model, in this model we used a three-dimensional convolutional neural network whereby we from the audio are able to compute a scaleogram that is fed into this model and is fed into the 4 residual blocks. In these residual blocks, we have the squeeze excitation layer, which is able to calculate weights and is able to reweight the features to see which features to pay more attention to. And then we have, of course, the identities added in the feature addition step in order to output a sensor. This makes sure that we don't forget how the data looks like. That's what a residual block does. So as the data is processed during these residual blocks, we see that more and more features, we're learning different features with each block. We dive deeper into the feature discovery until we reach the flattening layer whereby this tensor or this vector is flattened into a list, and then it's taken through the linear layer batch normalization, whereby this normalization to make sure that they're in the same range, you don't have really high or low features. And then for the physics branch or the symbolic branch, you find the 4 features of the rise, kurtosis, centroid, and skew are being fed into the model by the third arm, and the symbolic arm, and then they're fed into the multimodal fusion arm, and then the output is 3 classes. So with this model, the accuracy was 96%, and then you see which areas in the graphs did the model pay attention to, which area in the scaleogram had more prediction power, whereby the red parts represent the area that had the high prediction power. And then from these graphs, we're able to see how the model trained, and we're able to see that since they are smooth and following each other, there was low overfitting. So this is the confusion matrix that shows that most of the types were accurately predicted in their right classes. And then we find the final model that I had presented in the previous videos, whereby we have the partial discharge localization model. With this model, we are localizing, but based on the scaleogram. So once you use the scaleogram for localization, we find that the scaleogram is taken through one branch, through the one branch that is you can call it the neural branch, and you have the physics branch where the physics features are then fed into the fusion head or the localization head. So once the scaleogram is fed through the different convolutional layers, you see there are 3 convolutional layers, and the features are further discovered, or they're discovered and after being discovered, we have the pooling, whereby we are averaging all these features, and then we are flattening them to produce one list that is fed into the fusion head. The same thing happens for the physics features, whereby from the 4 features that we had put in, the features are expanded through the different layers to discover more hidden patterns or more hidden features to have these 64 features being concatenated in the fusion head. So from the fusion head, this information goes to the fusion head and the different linear layers until we have an output layer of the 2 coordinates. So we can see from initial training, the first iteration, we see that the performance wasn't good in a way that the validation the model wasn't learning, whereby the validation error reached a point and it was the same throughout. And then when we had a second iteration, we had an initial performance whereby the model was learning and the validation error the validation noise was declining until we reached a certain extent whereby the validation error increased. And then here in the distribution of localization errors, we see that the distribution is more of a central distribution whereby the localization errors are higher. We have a higher localization error. So from this conclusion, we see that the location of partial discharge is best done with a graphical neural network rather than a CNN-based model. And the graphical neural network model outperformed the other models, both in classification and localization. Why is it? It's because it shows that the different nodes or different microphones interact with each other in a way that the different waves can travel and reach the different microphones at different times and different speeds. So if we are able to capture that, then we're able to localize where the source of the sound came from, and we're able to also localize the type of sound we received. And the graphical neural networks captures these relationships well. The limitations that I faced was the class imbalance in the electrical data set, whereby we have the surface type having a lower number compared to the other number. So we had to carry out steps in order to fix this class imbalance. The next steps will be testing the deployed model on unseen data and fine-tuning the models according to these results. So we thank Mr. Galingwango for his teachings on machine learning that influenced the development of this work. Thank you so much.